Now that we've discussed what the electric field is, and we've seen how it looks for point charges, both positive and negative, we need to start thinking about how would you find it for more interesting situations. Generally speaking, you're not just in a situation where you have just one charge. You'll have 2 charges, 4 charges, 1,000 charges, 1,000,000 charges. And the way we're going to do it is we're going to use a concept we started to talk about last semester when we were talking about waves. I told you at the time it was going to become really, really important to us. You're going to see it again and again and again this semester. It's going to be almost as prevalent as Newton's second law was last semester. The principle in question is superposition. The idea that when you're trying to find the effect of a wave someplace or the effect of electric field someplace from multiple sources, you add them together. Superposition. So let's say that we have a negative and a positive charge someplace. Okay? I'm going to make the negative charge red and the positive charge blue because I firmly believe in my heart of hearts that protons are blue and electrons are red. The way you find the electric field someplace, say at some random point in space, like here or here, I'll go and do more points in just a little bit, is you take the electric field from each of the point sources separately. So there's going to be some field due to the positive charge there. There's going to be a slightly larger field here because it's closer. Okay? The negative charge is going to have a vector field that way. It's going to be the same since it's halfway between, and I'm assuming they're the same charge. The electric field will be in this direction due to the negative charge, more or less, trying to get it pointed kind of towards the negative charge. Now, superposition says we add these vectors together. So what does that mean? Well, for this one, it's going way that way, something like that. This one's going around like that, okay? And we can keep doing this. We can do some more points. Now, I'm not going to do the point right here because it's symmetric. I'm going to do a point over here maybe. This one's going this way due to this charge. And maybe right here where it goes this way really strongly. Okay? And maybe right here where it's going this way kind of weakly. Due to the negative charges at each of these points, this one's going away from the negative charge, so it's kind of this direction, but it's weak. This one's going towards the negative charge strongly. And this one's going towards the negative charge weakly. Okay? So if I add up those vectors, as we do with vectors, this one's going to go someplace like that. This one's going around here, pretty strongly in that direction. And this one is going about like this. Maybe like here. Okay? So we can keep doing this for a whole lot of points. What we're finding is when we get really close to the positive charge, the field tends to point more or less away from the positive charge, as you'd expect. This is dominating, so it basically looks like a positive charge. If you get really close to the negative charge is going to dominate, so we're going to have everything pointed like this. Okay? So if we go ahead and we connect everything up and kind of do the math, what we find is a series of lines that go like this, like this, like this, like this. And you guys have all seen this pattern before, as a matter of fact. Giving you the vectors, don't forget. This is a dipole. It's called a dipole because it's 2 charges, 2 poles. I'm going to clean it up and give you a clean version of it. The plus charge, the minus charge. There's going to be a vector that way, a field going like that, like that, like that, like that. This is what you've seen for magnets typically. When you played with magnets, back in elementary school in class, and you had iron filings, this is probably what you saw. Okay? Okay. Dipoles are really important because they crop up a lot. A lot of molecules have dipoles in them. I forget which way it goes, but either I think oxygen pulls more electrons towards it. It's got more electronegativity. So it likes electrons more than the hydrogen does. So the oxygen and water ends up being more negatively charged. The hydrogens end up more positively charged, and it forms a dipole. And that's actually what explains, for instance, a lot of water's cool properties. Okay. So that's how you find the fields due to multiple charges, okay? I'm going to give you one more example of this. I'm going to give you a whole sheet of plus charges. Okay, we're going to imagine there's not so much a whole bunch of charges, but, okay, oops, we're going to make it an infinite plane. Okay, not so much a whole bunch of positive charges, but an infinite number of them spread out uniformly, okay? There's formal mathematical ways of doing this, but I'm going to assert that the field has got to point, first of all, away from the sheet, and always vertically away from it, okay? The reason is, if we're going to go this way, for some reason, towards the left, there's no reason it should go that way versus the right, since both directions look exactly the same, okay? Any argument for it to go left should equally apply to go right, so the only way to point is straight up. Now, what's interesting is, and we're not going to mathematically show this, but it can be shown. I'm going to just tell you that the electric field everywhere, due to this, doesn't depend on the distance from the sheet. The basic reason is, as you get farther away from the sheet, go higher and higher up, the field due to any one of these charges is dropping off, 1 over r squared. But as you go higher and higher up, you're seeing more and more of the sheet kind of within your field of view. If you imagine you have a field of view like your eyes are seeing more and more charge, and so you end up with basically kind of a stalemate between the two effects, and you end up just having the exact same field as you go up. We'll talk more about that later. All right, that is enough for this video. I hope this has explained how you superimpose fields to find net total field, and we're going to practice with it a lot in the next few days.